Okay, so we're jumping into implicit differentiation here. So in implicit differentiation, this is where we look at functions that aren't functions anymore. So we're looking, sorry, functions was the wrong word there. We're looking at things like this expression here, which actually are a relation where we have x and y's both in our function. So we can have multiple variables in this space. Now, with this topic, we're going to start with just looking at the derivative with respect to x. So this left one here, you'll notice I've got d dx of this yn. So we're looking at, if we have a function, so if we've got d dx to the power to yn, it's not in the variable we want. So if we use it like the chain rule we did before, we would go, well, what about if we take the derivative of this yn with respect to y here, and then realistically, like the chain rule, these cancel out. We could do this as dy dx, and that means that the derivative of this y to the power of n we would apply it the same as we do another derivative. So the n comes out the front, y, and then n minus 1. So this bit's done, and then we have this sort of dy dx left over, and we're going to leave that there. Okay, you'll notice here in this other side that we've got the derivative of xn with respect to x. Well, we can just do the derivative of that. We don't need to leave this cumbersome thing out here. And so that's how we start with implicit differentiation. So we differentiate both sides of the equation with respect to x. So let's just... Also, when dealing with implicit relationships, dy dx is usually found in terms of x and y. To find gradient at a point, therefore, to find a gradient at a point, both x and y coordinate need to be known. So let's just jump straight into this. So I've picked a good example because this one allows us to do it. So the first thing is we've got to take the derivative with respect to x. So we go, let me change to a pen. We go d, now I'm just going to go d dx here, and we're going to be taking the derivative of x plus x squared y plus y cubed, and then this is going to equal d dx, and it's of 100. Okay, so let's break this into parts now. So we've got d dx, and our first one is just of x. Our next one's going to be the derivative with respect to x of x squared plus, not plus, x squared times y. Okay, and then we got plus d dx of y cubed, and this is going to equal the derivative of a constant with respect to x is always going to be 0. So we can put that as a 0 now. Now, this I'm stepping out a lot more than I would usually do because it's our first example one. So just bear in mind that if you were writing this, once you get your head around bits like this bit here, the derivative of that with respect to x, you can jump a step. Okay, but let's jump in here. So the derivative of x with respect to x is just 1. So we've done that in hopefully our methods course. Now this one here is our complex one. We've got a product rule. So we'll do this other side here first because it'll make a bit more sense. So I'm going to leave that one for a minute. But the derivative of y cubed with respect to x means we go, well, this is going to be 3y squared. We do the derivative of y with respect to y, and then we multiply this by dy dx. Now, this one here, what we're going to look at here is this, let me go to a pen. We're looking at this is going to be u, this is going to be v. And so if we remember with a product rule, we do u dash v plus uv dash. Now, in this, that means that the first one we do is the derivative of x squared. So we do 2x times y. Now, because we did the derivative of the x here, and it's with we're going in terms of x, we don't put a dy dx there. And so then we go plus for the product rule, and then we go x squared, and then the derivative of y is 1, but because we've taken the derivative of y, we also have to leave the dy dx there. Okay, so we've now got our function here. And so what we're going to do is we're going to take these values here. Let me go back 1 and 2xy to the other side. So we're going to be left with dy dx. And our common terms here, so dy dx has an x squared. So we've got an x squared with that. And then we've got plus 3y squared. And this equals -1 take 2xy. So all we need to do now is we just need to divide by both sides here. So I'm going to just put that, I'm going to just bring that up here so we can actually just keep working. Okay, so we've got that up there. So we're going to divide both sides by x squared plus 3y squared over x squared plus 3y squared. So they're going to cancel. So we've now got, on our final answer here, we've got dy dx equals -1 take 2xy all over x squared plus 3y squared. All right, so we've done that one. So that was probably more complex. So the product rule there, you've just got to consider, are you taking, if you're doing a derivative with which, so when we're doing a derivative of y and we have respect to x here, we have to leave that dy dx with it, or you might even consider a different variable there. All right, this next one here, so find the gradient of the tangent to x squared plus y cubed equals 5 at the point where x equals 2. So I've actually been a little bit ahead of the game and I've done a Desmos with this, but let's just consider this function here. So let's do implicit differentiation. So we're going to do the derivative with respect to x. So maybe I should move my picture down a little bit so we can do the derivative and then we can talk about it. So we've got d dx of x squared plus y cubed, and this is going to equal 2x plus 3y squared dy dx, and that's going to equal 0. Therefore, that's because so we've done the derivative of this side with implicit differentiation, and the 5 here is going to be, it's a constant, so the derivative is 0. So therefore, we're looking at dy dx is going to equal -2x over 3y squared. So we've got our function there, and then this continues here. This problem says at x equals 2. So we're looking here at 2, there's this value, and I can tell you it's going to be 1 just from looking at the graph. So we've got this value here of 2 and 1, but let's just double check. So that means here we'd be looking at x squared is 2, so we're going to be looking at 2 squared plus y cubed equals 5. And so we're going to be looking at y cubed equals 2 squared, which is 4. So 5 minus 4 gives us 1. Therefore, y equals 1. So we've got that coordinate there. Now, it said we're looking for the equation of the tangent. So now we've got our x and our y value. We know that at this point here, x is 2 and y is 1. That means we can use our function here, our derivative function, and we're going to be looking at, I'm just going to put a straight line here. Okay, so not quite hitting as a tangent there. So that's sort of this tangent here that we're expecting, and the gradient of this thing, the gradient will equal -2, and then our x coordinate is 2, and then 3 times our y coordinate squared, which is 1 squared, which means we're going to be looking at -4 over 3. Okay, which means that if we check this properly, or if it was done to scale, mine's not quite done to scale, we would expect to be going 1, 2, 3, 4 down, and then 1, 2, 3 across. So if that was the case, this here would be a better tangent, which you can actually see it is. So maybe I'll just delete that so it does not in our notes. There we go. So that's a better tangent there, which follows that value. So that's our implicit differentiation examples done. So good luck.